Hello Regina Sailing family and friends. So it's early in the morning, it's just a couple of minutes before 7 o'clock, maybe it's 10 to 7. So I'm up here and I'm ready to do some sights on planets and stars. So let's look what we have planned for yesterday, for this day, for this morning. So I'll do these plannings, I will do the exact shots here for this morning. So it's very useful to have these, because we know at what altitudes we shall set the sextant, in which direction we shall look, at what time. So here is my template for the actual shooting. So it continues the same way as the plan. So here's the real one. So here we have the stars and planets. So let's say that we have been able to shoot the Jupiter and the Deneb and the Antares, and we were able to shoot the Polaris. This star we never were able to shoot, it was not bright enough. So let's see if we can get something out of this. So what I can write, what you write here is the exact time of the individual shots. So let's say that we started off Jupiter, we left to the end. So we have here at 6 o'clock 57 and 12 seconds. Then we shot the Antares, we shot at 6:59:09, and the Jupiter we were able to shoot a little bit later, so that was at 7 o'clock and 2 minutes past 7 o'clock and 12 seconds here as well. So what did we read on the sextant? So of course we now check the sextant and read it, and since I am doing the exercise here, I'm cheating a bit, because I'm saying that, let's say that we shot the angle here at 18 degrees and 54 minutes. It's just something which is similar to this. And the Deneb we shot at 43 degrees and 58 minutes. And the Antares we shot at 26 degrees and maybe 42 minutes. And the Polaris, we shot it at the exact time. The exact time for Polaris is actually irrelevant. The exact time, we know what day it is. So we shot it here at 36 degrees and 38 minutes. Let's see if this exercise, this example, turns out to work for a demonstration how you do this. So all these yellow ones, that has to do with the sextant. So remember my template for the sun and planets. So this is step number 1, the measures. This is the yellow part. Then comes a blue part with the nautical almanac next to it. That is this part. Then we have some purple part that has to do with the sight reduction table. That is this part. And then we have the green, that is this part, to compare the altitudes. And then we have the Polaris has an own little calculation because it's so easy. So this is the same steps, but much less complicated than this. Can you see that? And that is because the stars here are so much easier to follow. I can just see that I wrote this in the wrong column because this is my second planet, but we don't have a second planet. So I'll write Deneb here at 6:57:12 and 43 degrees and 58 minutes. So I can use the eraser now. I've used the eraser before, but you haven't seen it, folks, because I switched off my camera when I've done my mistakes. And I have done the mistakes here and there, but this is how it is, and I'm not a genius, and I have invented all these calculations myself. sitting at a table instead of doing it in real world. So I'm really eager to get out sailing again in summer to do some sights in the real world. So the planets, you can see that they go down here, and then there's a gray field here. Use planet performer instead. Okay. So the Jupiter is similar to the Sun. So the planet performer for the planets is very similar to the Sun with some differences in the corrections. And the stars, they go straight down here. Okay, shall we start? Well, let's first look at the measurements we did on the sextant. So we'll say that the index error is 4 minutes off the arc on this sextant. So that's always the same, of course. So 4 minutes off means that you have to put it back on. So you add 4 minutes, you add 4 minutes, and you add 4 minutes, and you add 4 minutes. And here you can see how much sense it makes to do this preparation and to do all these planets and stars at the same time. And the good thing is, at the very end, you will get a nice fix, hopefully. So now what is the observed altitude? That means that we have to add these together. So that's 18 degrees and 58 minutes. This is 26 degrees and 46 minutes. This is 43 degrees and... oh, no, it's not. No. Another time for the eraser. Because 4 minutes added to 58 minutes means that we have gone one more full degree there. It's 44 degrees and 02 minutes. And here it's 36 degrees and 42 minutes here as well. So, very nice. So what's the dip? Well, the dip is with the height of the eye. So shall we take my boat again, or shall we take something else? Well, we can say we are in a smaller boat this time. We are 2.5 meters above the water level. Look at the yellow page. We look at 2.5. It's in between 2.4 and 2.6. So that means 2.8 minutes that we have to deduct from the section, and that is because the height of the eye, that the horizon is further away. What did I say? Shouldn't have talked in between. I said 2.8. So that means 2.8 minutes. We deduct them. 2.8, 2.8, 2.8 minus. They're always negative. So we then correct for the apparent altitude. So we deduct this. So that makes 5. That's 5. 18 degrees 55.2. And here it is this much. 3, 4, 26. Hope that's right. And here we deduct 2.8 as well, so that is 2 and 9. No, you can't have 9 here, because that is, of course, that is 50, because it's 6 degrees to a full minute. So it's 43 degrees, 59.2. You can make a check to add the 2.8 there, and it should be the right one. Yes. So here we deduct it from here. So we deduct that, and then it becomes 9 there, and this is 3, 36 degrees and 39.2 minutes. Goody good. So now the refraction. Now that depends on the angle that we have shot it. So this is not the same all over these various shots, because it depends on the altitude. So let's see in the first example. And you can see here, now we look at the middle here, stars and planets. So that means that we do an apparent altitude, which we have here at 1855. So 1855 is somewhere, 1855 is in between there. So that's minus 2.8. Minus 2.8. And then I can write this down here. Minus 2.8. And then we have to do monthly correction also for Venus. But it's Jupiter we are shooting. There's none for Jupiter. There's none for Jupiter. But for Venus, you, depending on the time of the year, you then have to do a little correction furthermore. So Jupiter has no correction at all. That's good. So we can write the monthly corrections 0 here. So when it comes to the stars now, so we have an apparent altitude of 2643. So it is here somewhere, 2643. It's in between here. So that would be minus 1.9. Minus 1.9. Here we have 4358. We look here, 4358. It's in between those two. Can you see that? 4253. So it's minus 1. Minus 1 minute. And then for the Polaris, we have measured it at 36.36 here, 3639. 3639. It's somewhere in between there. So it's minus 1.3. Minus 1.3. And there are no monthly corrections to take into consideration when it comes to the stars. It's only the planets that have a monthly correction here. So let's do this calculation there. So that means 4, 2, 5. So we have 18 degrees and 52.4 minutes. And we had no monthly correction, so we can write that down here, 52.4. Now the Antares, here we have the refraction of minus 1.9. Because we shot it at a little bit higher altitude, the refraction is smaller than this. Because if you remember with the refraction, if you measure it 90 degrees, you don't have a refraction at all. And the closer to the horizon you get, the more the refraction is. So if you shoot anything under 10 degrees altitude, you should refrain from that. So let's do this math here. So, and that's 2, 1 there for 26 degrees, 41.3. Here we deduct 1. Lucky me, very easy to do. 43. And here we do like this. That's 2, that makes it 7, 3, and 36 degrees, 37. So these are the true altitudes, which I then can copy down here as well. And why do I copy it? I don't know. I think it is so you can write it in a nice manner, readable. So for the Jupiter, we would go down and use the planet performer. We can do this, and then we can continue with the stars, which goes down here, or we could do the stars first. Let's do the stars first because it's new, isn't it? So we'll do the Antares. So we measure the Greenwich hour angle of Aries at full hour, and now they have different times, these two, and that is why we need to look at that here. So we look at the Greenwich hour angle on the 26th at full hour, and the full hours is 6 hours. So look here, 6 o'clock. There we have 6 o'clock, 2:45 and 33. 2:45, 33.6. So I'll write this down here, 2:45.33. 33.6. This is 6 o'clock as well, so that means that it has actually the same Greenwich hour angle. And here, well, we should actually know the time here. I said that it doesn't, we don't need to have the exact time, but we can actually say it was at 7 o'clock here. 7 o'clock, because it doesn't change much the corrections, but we need to know the approximate time. So at 7 o'clock we have a Greenwich hour angle at 260 36.1. 260 36.1. And now we need the increments of the areas, and that is 59 minutes and 9 seconds. So we look at the back here. 59, it's almost a full hour. 59 minutes and 9 seconds. So 59 and, what did I say? 9 seconds. Here we go. Not sun and planets, but the increments for areas. So that's 14 degrees, 49.7. 14 degrees and 49.7. So how about 6:57:12? 57, 12 seconds here. You look at areas. 12, second column, 14 degrees, 20.3. 14 degrees, 14 degrees, and then, what did I say? 20.3. So that, what is the Greenwich hour angle for areas? Well, we have to add the Greenwich hour angle for the full hour plus the increments. So that is, you're getting very good at counting in your head, really. So that's a 3, and that's a 3, and that is 4, 5, 6, 7, 8. So every 60 minutes is a degree. So if you have an 8 there, you write it 2 instead, because you get a full degree here. And the full degree there is 5 plus 5 is 10. 4, 5, 6. So 260 degrees and 23.3. And that makes sense, because here we are just before, 1 minute before the full hour of 7. And here we have 7, so that's 260 degrees and 36. Let's see what the Greenwich hour angle is for Daneb, or better, for the time 6 hours and 57 minutes and 12 seconds. We add these together, that becomes a 9, that becomes a 3, and that becomes a 5, and a degree sign, that becomes a 9, that becomes a 5, and a 2. 259 and 53 minutes. Does that make sense? Yes, because it's a bit earlier we shot that than the Antares. So now we need to choose a longitude. Now, since we have a westerly longitude here, what we need to do is that we choose a longitude which is pretty close to what we think that we are, but it should have a 23.3 in the end, because you don't want to have minutes, only full degrees. So if you want to have, it needs to be, the chosen longitude needs to be 23.3, because when you subtract these two, then it should become 0. Remember, when you have easterly, you should add instead. So here is my footnote number 8, talking about that you remember that it can be plus or minus depending on if you have westerly or easterly longitude. So it needs to be 23.3 minutes here. So when you deduct it, it becomes 0. But what do we choose which has 23.3 in the end? We can take, if we do 11 degrees here, 23.3, we are pretty close to what we think we are. This is our chosen longitude, And that chosen longitude is in a red box because that's what we're going to draw in our chart later. 11 degrees, 23.3, that's good. So what's the local hour angle? We deduct all these nicely, so it becomes 0 there, and that's why I have made a little degree sign there, so it's only full degrees, so it will be 249 degrees, local hour angle. Now, it could be a little bit different, 249, if we choose a longitude which has another full degree here. But it should be quite similar to the chosen over there. So here again, we have a Greenwich hour angle at 259 degrees and 53.9 minutes. So we should have something here as a chosen longitude, which has 53.9 in the end. So we need to choose a longitude which has 53.9 in the end, but which is pretty close to 11 degrees and 36 minutes. So if we write 11 degrees 53, that's pretty close to 11 degrees 36 minutes there. So that means that if we deduct this, we get again 249. I really wanted to show, was my idea, that we can get something else there. If we had chosen 12 degrees there, for instance, but it wouldn't make sense in this case. Okay, so that's that. And here the Greenwich hour angle of the, it's the same thing. So we have our Greenwich hour angle of areas, which is approximately 260 degrees and 36 minutes. It doesn't really matter because it is more approximately. So we have some 11 degrees here and 36 minutes. That is, we need to get a local hour angle. And the local hour angle here is then 249 degrees. No surprise, because that's what we have had that before. Good. So now we have chosen our longitude. So now we want to choose our latitude for the morning. We've done that many times again. It is 37 degrees. Now we go into the volume 1 of our sight reduction table. Volume 1 is about the stars. And we will look up these stars and what ZN and what HC they have. That is so nice. So we have our latitude of 37 degrees. We have our local hour angle of 249, which actually all happens to be around the, you can see here, which happens to be exactly around Twilight. So that's when we shot it. So Deneb, we have 44 degrees and 5 minutes. That's the height. 44 degrees. Deneb is now here. So the 44 degrees and 24 minutes. 44 degrees and 5 minutes. Sorry, that's my razor. I have to be able to read 44 degrees and 5 minutes. The azimuth is 59 degrees. Okay, and the Antares, it's again the same local hour angle, 249. There is Antares. So we will find here, it says 26 degrees and 31 minutes. 26 degrees and 31 minutes. 81 degrees, 181 degrees. This is the real azimuth. So the azimuths are in red. So they we put into the chart as they are. So that's very practical. But I've chosen to have the HC below the azimuth in this template, because then I can use my true altitude here, which comes from here, what I have actually measured. And you can see that the actual altitude that we measured was 26 degrees and 41 minutes, never mind the 03. And here we have the altitude of 43 degrees and 58 minutes. Here we can see that the observed altitude is bigger than the calculated altitude. So since we have measured a bigger altitude than we should, we saw it bigger. That means that we are closer. So we are towards. So I write towards here. And here we can see that we measured the angle, or the observed one, less. It's smaller than the calculated altitude. So since we have measured less, we are further away. So I write away. This is also in red, so these boxes are important because they go into the chart. Now, how much is the intercept? That's the difference between HC, the delta between HC and HO. So here it is exactly 10 minutes, which means 10 nautical miles. And in this case, it is 7 minutes, which means 7 nautical miles. So we can draw this in a map, in a chart, or in the template, which I will show you. And so we have our position at our longitude and our chosen latitude. Then we have an azimuth of the body and how many nautical miles we are towards or away along the azimuth. And then we draw 90 degrees of that a position line. How about our latitude? So the latitude, we need to have the different corrections. So I've found in my wonderful blue nautical almanac the page 274, which has to do with the Polaris calculation. So here we have 274 with the local hour angle of areas starting at 0 and continuing and continuing and continuing. It's actually continuing even on the next page, because that's where we want to go, because we have a local hour angle of 249 degrees there. So 249 degrees is in this column. So these are all the local hour angles between 249 and 240 and 249. So we go down here. This is 249. So the first correction that we have to apply is 1 degree and 34.3. So I write this here. 1 degree and 34.3. That's the first correction. The second correction is that we get when we go in the same column, go down here and look at our latitude. So our latitude was about 35. So that's in between 30 and 40. So it is about 0.6, hardly any difference. But A1, the correction A1 is 0.6. I'll write this here, 0.6. Then what we do is that we continue down the same column until we get to the month. It was February, so I have another correction, 0.4. That's the A2 correction. What did I say? February 4. So now, in my template, I have said that I have to add all these corrections. So that's what I'm going to do here. So all these corrections are 1 degree and 35.3. And the latitude is the observed altitude here plus these minus 1 degree. So that means that since I have to deduct 1 degree, it's already written here, this 1 degree. So this is the degree, so to speak, I should deduct. So we can take this away, and then we add the 35.3 minutes to the altitude up there. And you can see that I've made a yellow little weak line there. So this gets down to here as well. So we add it. So we add these. So 9 plus 3 is 2, and then we have 7, 8, 13, and 3 plus 3 is 6, that's a full degree, and then 1 from there. So 1 more degree here, so it's 37 degrees. So our latitude is 37 degrees and 13.2 minutes So that's one line that we can draw, one position line, which is very easy, because that's our latitude. I hope you got this thing that I deducted this 1 degree. I have to add A0, A1 and A2 and then deduct 1 degree. So I've added it all together and then I deduct that 1 degree. So that's how that comes. So all that we need now is to do a calculation of the Jupiter and then draw all these lines. So we will get 1, 2, 3, 4 position lines. Well, hopefully they cross somewhere. So I have my planet performer here. So it is the planet in question, Jupiter. The date is 26th of February. My approximate latitude, that is said here, 36 degrees and 47 minutes. My approximate longitude, 11 degrees and 36 minutes. This is north, this is west. The time that I shot Jupiter was exactly at 7 hours, 2 minutes and 12 seconds. Then I can write log and speed over ground. That is not so important now because we have so many position lines here, so we don't have to transfer the position line. So that is easy. So here it says the sextant angle. I can do this calculation again to get the true altitude. And then it says, or do on Twilight performer. So here this is my Twilight performer. So this is exactly the same thing as this. So we don't have to do it again. So we can just copy the observed altitude from here. So that is 18 degrees and 52.4 minutes. So now what we do is that we get the information about the position of the planet and the ship. So the working latitude, well, 36 degrees 47 minutes. Well, the closest there would be the 37 degrees. So that's in red. That goes down here, 37. We draw that in the chart. Then we have the declination. So we have the declination at full hour for this planet. So we look up in the daily pages on the 26th and the full hour, and we shot it at 7:02. So full hour is 7 hours. It's can you see it? No. 7 is there. So this is Aries, right? Aries. We don't want Aries. We want Jupiter. As that column there. It's this column. So we go down that column there, and we look at 7 o'clock. That is there, 7 o'clock. So it has a declination of 22 degrees and 6.7 minutes south, and it has a Greenwich hour angle of 330 degrees and 11.4. So the declination was 22 degrees and 6.7 minutes south. And we are at northern latitude. The Greenwich hour angle was at 7 o'clock, 330 degrees and 11.4 minutes. Now we need the increments for the planet. Now the increment for 2 minutes and 12 seconds. The increments for 2 minutes here. 2 minutes and 12 seconds is down there. So the increment for sun and planets for 2 minutes and, what did I say? 12 seconds is 33 minutes. So I'll write this down here. 33 minutes. 0.0. And now we have the V factor. Well, this is something new, because the V factor is because the Venus is not so accurately exact as the Sun is. So what we do is that we go back to our daily page here. This is the column of Jupiter. So we look at the column of Jupiter. So we go down all the way down there. And there it says it has a V factor. So that means that it has been a bit faster than you would expect it to. So we have the time, 330 degrees and 11.4 minutes. And here it says 345, 13.3 minutes. That is in 1 hour. So you can see that it's not a straight, exact 15 degrees for that hour. So it's 15 degrees and a little bit more. Because otherwise it would have said here in the next hour 345, 11.4. But it's 13.4. So it's a little bit more. It's about 2 faster there. So this 2 minutes faster we have to take into consideration, and that's not difficult at all. So we look at this 2 minutes on the increments, and we see how much does this 2 factor mean for 2 minutes. Never mind the seconds. So all this here, all the V or D correction is valid for 2 minutes. So how much faster is it than the standard? Well, if the V factor is 2, it is, for these 2 minutes, only 0.1 minutes faster. So we have to add 0.1 minute to the increments. So we have now the V factor, which is a new thing that we have to take into consideration for planets. We add these. So we add all these. 4 plus 0 plus 1 is 5 in the end. So here we have 1, and there we have 4, and then we have 4, 330 degrees. So that's the greenish hour angle at the time. So for planets, you have to take a little bit into consideration that they are a little bit faster. Sometimes they are slower. So you have to check if they get faster or slower than these 15 degrees per hour. Now we'll choose a longitude now. So we'll choose a longitude that the local hour angle becomes 0, 0, 0. So we say 44.5 in the end. So our longitude we think is 1136, but we shouldn't say 36 in the end. We should say 44.5. So that's why we say 1144.5, because if we now deduct it, we have minus. So if you read off on the footnote number 13, that says that if we have western longitude, which we have, then you take minus, because you are always interested to know the local hour angle, which is the angle in between us and the body in the sky. And on eastern longitude, you would add these two. But we are on western, so we subtract them. So we subtract, it becomes 0. So here we subtract from, that becomes 9, and this becomes 2, and this becomes 3. So we have 300 and, no, that's wrong. That's wrong. Sorry. I don't even have my eraser now. So it is 319 degrees, of course. So that's my local hour angle between us and Jupiter. So that's good. Now we go into the site reduction table of the said 37 degrees. We find a working latitude of 37. We look if it's same or contrary. Well, we are in northern, they are in southern. So we are on contrary here in these hemispheres. So we look at the declination range. So the declination range of 22 degrees, it's this one. So I'll find that in my site reduction table. So here's my site reduction table. I have found it for latitude 37 degrees. We are on contrary, and we have the range here. So that means that we are now looking at a declination of full degrees of 22. That is here. We have the local hour angle of 319. You can't see it, but I can tell you it is here. It is the second highest. So I go in this column and I'll read off those figures. So here now it says that it's 19 degrees and 29 minutes. That's the altitude, HC, that we should calculate for the full degree of declination of 22 degrees. It's not really 22, that's why we have the D factor, minus 50, to take into consideration. And the Z, which is not yet the azimuth, is 140. So I copy this here. The HC is 19 degrees and 29 minutes. The D factor is negative, so that's 50. And the Z is 140. So this 19 degrees and 29 we copy up here, 29. And then the question is 50. This is the weight, 50/60th we should take of the declination of 7 minutes. Let's call it 6.7, 7 minutes here. So that's why we need to go into table number 5. And I will find table number 5. So here is table number 5. There we will look at the D factor, which is 50. That's here. That's an old exercise. 50. And then we go down here to find the minutes. And the minutes is 7 minutes. So here we have 7 minutes. So I go on that line there. So the 50/60th of 7 minutes is 6 minutes. I could have done that in my head as well. So that is 6 minutes. 6 minutes. And since the D factor is negative, this is negative. So the corrected altitude is 19 degrees and 23 minutes. So that is HC. So we compare HC now, the 19 degrees and 23 minutes, which are pre-computed, with what we actually measured, 1852. So we measured a smaller angle than 19 that we should, 1923. So since we have measured a smaller angle than we should, that means that we are further away. So we can already say that we are away. And then we put the bigger number on top here, 19 degrees, 23 minutes, and the smaller one down here, 18 degrees and 50, let's call it 52 minutes, and subtract these. So that is 3, because there are 60 minutes to a degree. And this is 0, 0. So it's 31 minutes, and 31 minutes is, of course, 31 nautical miles on the surface. So we can say that this intercept is 31 nautical miles. Now, how about the azimuth? Z is 140. So if the local hour angle is bigger than 180, well, it is, it's 390, the Zn, the azimuth, is actually like the Z. So yes, we don't have to do any calculations. The 140 degrees is the azimuth. Makes sense, because the Jupiter we shoot in the morning at 7 o'clock. So in the morning, it is a morning star, a morning planet. So it goes up a little bit before the sun. So that's why it is 3 hours ahead. But nevertheless, it rises here in easterly direction. So that's southeast, so that's nice. So we have an azimuth of 140. Our working longitude, well, that comes from here, 11 degrees and 44.5. So now we have all these things. We have this we can draw, which is a azimuth and position line 90 degrees to that. We can draw the azimuth and the position here as well, taken from the stars, and we have a latitude taken from the Polaris.